Okay, so good afternoon. We're moving on now from our igneous rocks to the other part of the rock cycle that I discussed in our previous lecture, which are the rocks formed by surface processes, so our sedimentary rocks. You may have talked about sediments in G101 before. So these are particles or chemicals that accumulate on the Earth's surface. If they get the chance to be buried and turned into rocks, then we call them sedimentary rocks. And they're really, really useful tools for anyone who's interested in the past, or indeed the present, because they can tell us about ancient sedimentary environments. And a lot of people find sedimentology, which is the study of sediments, a lot more easy to get their head around than some of the other geology types, because you can see the surface processes happening today. All of the processes I've told you about plate tectonics and igneous rocks and magma chambers, some people find that hard to get their head around because they can't see a lot of it. But sediments, you can see all of these processes I'm going to talk about. If you just take a stroll along the seawall, you'll see a lot of sediments accumulating around the mangroves. So they're very fine-grained sediments. They contain a lot of organic matter. If they gradually get buried and turned into rock, we can look at that rock and, being detectives that we are as geologists, we can tell that it came from an ancient mangrove. And this is why we study sedimentary rocks. Well, one of the reasons why. So just as a summary slide, so introduction to sedimentary rocks, they're produced from the weathering products of pre-existing rocks, or biological matter. We can mainly divide them into 3 or 4 types, which I'll come on to later. So our plastic sedimentary rocks are produced from sediments that are made up of fragments of pre-existing rocks or minerals. So our solid particles. Chemical or geochemical sedimentary rocks, they're produced from grains or crystals of minerals that are precipitated out of seawater usually, or water rather, any type of water. And organic rocks are those that are made up of actually living tissues. So we're talking about oil, we're talking about gas, oil and coal are the main ones. And a lot of the structures that we see in sedimentary rocks, whether that's ancient burrows, whether that's ancient fossils, whether that's ancient ripple marks, can tell us a lot about that past sedimentary environment. So just like a forensic scientist going to a crime scene and looking at footprints and looking at things left behind, that's exactly what we're doing here. And when we talked about our geological timescale before, all that was built up by looking at fossils and sedimentary rocks and matching up rocks across the land, so we can tell that they're the same age by looking at the fossils. And another really, really important reason for studying sedimentary rocks is that this is where the majority of our resources come from. Sedimentary rocks are incredibly important for producing oil, holding oil, and keeping hot oil underground. Whether you're into oil or not, we still use it. But also water. A lot of aquifers underground are formed in sedimentary reservoirs. I have to apologise as well, I've been sick all week, so if I start coughing and, I don't know, fainting, then I'm sorry. This is just an example of a sedimentary structure that I'll come on to later. So I'm sure you're all familiar with ripple marks that are produced in beaches or on the bottom of rivers today. If these get buried, they can be preserved in the rock record, and we can see them. These are some nice ripple marks in Nandi. And we can do nice things with ripple marks. We can tell if they're asymmetrical, which they are. We know the current came this way. So these were produced in a river or a water environment, and we know the current came this way. I've talked about Everest before. I've told you that the top of Everest is a limestone with a marine fossil in it. We can look at that limestone and tell exactly what sedimentary environment those rocks were formed in. And a lot of sedimentary rocks as well, they're very climate dependent. So some sediments only form in certain climates. So by looking at ancient rocks, you can tell what the climate was like in that part of the world in the past. So I come from South Wales, which is now about 55 degrees north. It's a temperate latitude, it's not in a tropical latitude, it's not very hot, I can tell you that. It rains all the time. But all of the rocks along our coastline are filled with fossil corals. And we know now from looking at the distribution of corals, they can only form in the tropics and subtropics. We also know now that Wales once lay at the subtropics and tropics. And a vital clue for that was the fact that we saw these corals in the rocks formed along the south of Wales. And they're quite important if we're going to understand our planet, because even though they make up by volume only 5% of the crust, they cover about 2/3 of it. The main reason for that is that the oceans cover much of the Earth, and the oceans are blanketed with sediments in most locations. So let's first go back to sediment. I told you we're talking about particles or crystals. Basically, they're weathering products. They form from the weathering and erosion of pre-existing rocks. And that weathering can either produce solid particles or it can produce dissolved particles in water or air. So the sediment can either form by the removal of solid particles and the deposition somewhere else, or the dissolution of pre-existing rocks and the precipitation of those minerals elsewhere. And you can't see that diagram, I'm sorry. The main way we tend to describe and classify sediments is to do with their grain size. And you have to get used to these terms. Forget the numbers for now. You may have covered this in GE 101 anyway. These are our main categories. So we classify all sediments bigger than 2 millimeters in size as gravel. And we can break those sediments down into pebbles, to cobbles, to boulders. Sand. Okay, in everyday life we refer to sand as what's on the beach. But in geology we refer to sand as something very specific. So 1/16 of a millimeter, so 0.11 decimal, to 2 millimeter, we call sand. Silt is 0.039 millimeters, I think, to 1/16 millimeters, and clay are very, very fine particles. We sometimes call these mud as well. And some other really important terms, whether we're talking about our clastic sediments, so our fragments of pre-existing rocks, or we're talking about our chemical or organic, all will have a source area, this is where the sediment originated, and a sink area, where it's deposited. Chemical sediments might have a very short distance from the source to the sink, but plastic sediments tend to have a very long distance. This is an example of a nice meandering river. And these are the main processes we talk about when we talk about sediments. And I'll show you a nice diagram. So if we start right at the beginning, so we have some nice rocks here that have been exposed to the atmosphere, to climatic impacts, to weather. They can get weathered, they can get broken down by different processes. We call that weathering. And there are two main types of weathering. So we talk about chemical weathering. So this is where the minerals are chemically altered or dissolved. This is really, really common. I've mentioned this before. Rainwater has dissolved carbon dioxide in it because the atmosphere contains carbon dioxide. When you dissolve carbon dioxide in water, you produce carbonic acid. So rainwater is slightly acidic. Around cities, particularly around cities that produce a lot of coal, and therefore they put a lot of sulfur in the air, you also get a bit of sulfuric acid. But rainwater can often be acidic, and it can dissolve any rocks, particularly limestone. If you remember from your practicals last week, limestone is predominantly made of calcite. We all drop the acid on the calcite, it dissolves. So the same thing happens with rainwater. Physical weathering is simply a mechanical process where rainwater, where rivers, where ice can actually break apart rocks, and then they can be removed by erosion, generally under gravity or by a current. And these are interlinked. For example, if you break down particles by physical weathering, they have a greater surface area for chemical weathering. If you chemically alter something, it might be more susceptible to physical weathering. So these are really interlinked. And chemical weathering is incredibly important in warmer temperatures, because as we all know from chemistry in high school, if you increase the temperature of the situation, you increase the rate of a reaction. It's the same with chemical weathering. So you tend not to have much chemical weathering in very cold climates. In warmer climates, you get much more intense chemical weathering. The next part of the process is erosion. So the difference between the two, this is the breakdown of pre-existing rocks. This is the removal of the sediments produced. And then we have various different currents, various different mediums, air, water, wind, that can transport that sediment. And eventually the situation might arise where we deposit that sediment, or we change the chemistry of the environment so we can precipitate out our chemicals. And this part really is key. A lot of sediments are produced on the earth, and then they get eroded again. They never actually go on to form rocks. And the majority of sediments that are deposited on land, they eventually get eroded, because we've got net erosion on land. Most of our sediments collect in the oceans, because they're not as easily eroded. But if they get the chance to be buried, then a series of chemical and physical processes can turn them into rocks. The diagenesis is the process by which physical and chemical changes may change the sediments into rocks. We call that process lithification, literally the formation of rocks. Just to talk about that chemical weathering as well, you see a lot of this in Fiji because you have a lot of limestones here. Because most islands are surrounded by reefs, which are made up of calcium carbonate, they might go on to form limestone. So when they get uplifted, you get a lot of limestone scenery around the South Pacific, which is susceptible to dissolution by rainwater, and we can develop what we call karst topographies. We might get caves underground. There are a lot of caves in Fiji, so rainwater trickles down through cracks, it dissolves the limestone. Eventually it might come underground and actually dissolve away more limestone caves. But this scenery is quite common in Fiji because of the number of limestone. That's just an example of chemical weathering. So when we're transporting our sediment, I've already talked about weathering, lots of things can happen to that sediment. I'm mainly talking about particles now, not the dissolved chemicals. That's a slightly different process. But when we're removing our sediment by water, wind or ice, we can transport it great distances. We might transport it just a little way, but a lot of sediment travels quite a long way. And as it's being transported by water, wind or ice, various things can happen to it, depending on the process. So we might actually get, especially in water and wind transport, our grains will bash together, they will abrade against each other and they'll become more round. We call that rounding. We also might get sorting of our sediment. You imagine larger grains can be less easily transported by wind, water or air. So if you have a current transporting a mixture of grain sizes and then the current becomes weaker, then it's going to deposit its larger grains first. So you'll have a layer of large grains and then the finer grains will carry on transporting in solution. That current dies off a little bit again. You'll get your medium grains deposited, and the finer grains can continue. So it's a process of sorting sediment. You're organising your sediments as you're transporting them. And the further you transport sediment, the more likely you are to have grounded the sediment and to have sorted it. And because most of this transportation occurs under gravity, and the steepest slopes are up here, so our fastest currents at the beginning of the transportation process, generally speaking, the further you transport sediment, the finer the grain size, because you've had more opportunities to filter out your larger grains as the current goes on. And just to give an example of just that process from mountain to sea, mountain streams tend to have higher energy, steeper slopes, so you can transport a lot more pebbles, much larger grain sizes. And just to give you some background, transportation is not a continuous process. You might get a severe rainfall event and you'll move your pebbles and then maybe those pebbles will move for another year. or they might move gradually just once every couple of weeks, depending on the rainfall and the climatic conditions. It's not a continuous process. As we go down, I'm just using rivers as an example, we tend to get finer grains, we've got some medium currents, we can't carry these grains in suspension anymore, so we deposit them upstream. By the time you get to the sea, you've only got very weak currents. They can't transport the coarser grains, they've already been dumped upstream, so you're left with your very, very fine grains. And by the time a river gets to the coast, generally speaking, it's only carrying very fine grains, with everything else being dumped further upstream. And if you're looking at modern sediments, just to give you an eye of what we're talking about when we're sorting, this is a really nice example of a sand that has been quite well sorted. So most of the grain size, they're roughly similar sizes. Whereas a very poorly sorted sand could look like something like this. Or even worse, it might be huge boulders and fine clay. This is just an example. And the terms we use when we just describe roundness, so well-rounded, this is where they don't really have any corners, they will be knocked off by abrasion, and we call these angular, where you can see lots of corners, they haven't been rounded very much. And just thinking about different transportation mechanisms, if you have a glacier and it's picking up particles, squeezing around particles, ripping them off the bedrock, and transporting them downstream, because ice is a solid, those grains aren't bashing against each other, so they won't be abraded. So when a glacier melts and deposits its sediments, the chances are they're going to be very, very poorly sorted, because they haven't had that chance to be filtered off, and they're also going to be very, very angular, because they haven't been abraded against each other. However, if we think about wind, Singatoka sand dunes, for example, those grains are constantly being blown against each other. They're knocking off corners. So desert sands tend to be quite well rounded. And these are all things we can look at to give us clues about how those sediments formed in the past. So eventually, once we've transported our sediment, they might be deposited. That might not be their final destination. Once they're deposited, they might be eroded and transported again and deposited somewhere else. We call that the whole process reworking. Sediments can be reworked or reworked or reworked. But eventually, those sediments might either settle out, or you might get a large-scale accumulation of something in place, so organic matter, or you might get a chemical change that causes ions to come out of solution. All of those things are called deposition. And the environment of deposition, so the nature of the situation, the landscape, the processes, the climatic conditions, they dictate what sort of sediments we see in the environment and also any sedimentary structures. So we can look at sediments and say, okay, that was deposited in an alluvial sedimentary environment, which is a river and its banks. And there are lots and lots of different sedimentary environments within this. So there are many, many diverse different types of sedimentary environment on land. So a lake is a really nice sedimentary environment because lakes are calm, they don't have currents running through them, so sediment tends not to get washed out. So lakes are incredibly useful for looking at records of changes through time because they tend to collect sediment without eroding it and washing it out. And one thing you can do as a volcanologist, and one of my colleagues, Eleni, he's from Samoa, and he went to Samoa and he found a lake. It's quite an ancient lake. He took a core of sediment through that lake, and he looked at the different ash layers in that lake. And he dated those different ash layers, and so he now knows how frequent volcanic eruptions are in that area, and they occur quite regularly. So in terms of assessing volcanic hazards in an area, lake sediments are quite useful. They're also useful for many other reasons. You can look at climate records through time. A colleague, Michelle, she actually looks at the remains of non-biting midges, so tiny flies, called chironomids, and the different species of chironomid can tell you about climate conditions, so you can tell changes in climate through time. But because lakes, they're quite low energy, they don't have many currents, mud and silt can settle out of them. The very, very fine particles. They're very hard to make them settle out, so you need a very, very low energy environment. So you tend to find a lot of mudstones here. And maybe organic matter that's washed off from the hills, etc., etc. Rivers, these are incredibly dynamic sedimentary environments, and they vary incredibly in terms of what sediments they dump high in the stream and towards the sea, maybe because of energy, because of the gradient of the slope, but river sediments can be hugely variable. They also might have organic matter in them. The further you go from the source, you tend to remove your less resistant minerals to weathering. So you tend to have a lot more like quartz, which is quite hard, towards here than up here. Desert lakes, so in desert environments you don't really have much water, but if you have your seasonal or annual floods, you can produce desert lakes. Of course, in desert environments there won't be much organic matter. There'll be very, very intense chemical weathering because of the heat. So you get very different types of sediments. In glaciers, you get very different types of sediments again. If you go towards the shoreline, we talk about deltaic sedimentary environments. We talk about beach sedimentary environments, and those two are very, very different. So near a delta, that also tends to be quite low energy. You get a lot of fine-grained sediments spread out, whereas at the beach you've got a lot of wave action, so you tend to have more rounded, more sorted sediments, because you have a lot of waves action on the back. And as we move into the sea, things change again. Our continental shelf, which is our extension of our landmass, is quite shallow gradient. We don't get very strong currents, apart from in the nearshore area where we have waves, until we get to the continental slope. And then we have these spectacular, I don't know if you've seen photos of these, we didn't know they existed till the early part of our century, these huge canyons which transport sediment from the continental slope onto the ocean floor. They're caused by turbidity currents, and they carve out these incredibly deep, kilometre deep canyons in our continental shelf. And I won't go into this too much, but each of those different sedimentary environments has some very, very distinctive sediments associated with it. So if you could go back and read that, that would be great. We'll cover it in later lectures anyway. So once that sediment has accumulated, it might be eroded again, or it might be buried. And then with increasing temperature and pressure, because temperature and pressure both increase as you go deeper in the earth, you can do many things. You can squeeze out the water and air between your particles. And actually the water between these grains might start precipitating out. And it might actually cement the rock together. So we call those processes compaction and cementation. And they're really, really important for converting sediment into rock. And depending on what sediment you get at the beginning, you'll get a very different rock. So I talk about mud, the very fine grains, that produces a mudstone or a shale. Sand grains will produce a sandstone. Gravel will produce a conglomerate or a breccia. And if we have organic tissues, we produce very, very distinctive types of sediments or sedimentary products. All of these we'll cover in later lectures. And this is a very close-up. You might see some of these in your later labs if I can set it up. And this is a thin section. So I've mentioned before, you can polish a rock to 30 microns thickness, put it under a microscope and shine light through it. You can see our nice textures. These are our moderately rounded sand grains here made of quartz. And between them, you can see they're nicely cemented with calcium carbonate. And by shining different light patterns through them, you can tell by the colours that it is calcium. So, as I've talked about before, there are many different types of sedimentary rocks. They're loosely divided into our plastics, our biogenic chemicals, organic chemicals. I'm not going to talk too much about these because they fall between igneous and sedimentary anyway, so I'll focus on these, and I'll focus mainly on this type today. So yeah, our plastic sediments, these are formed from our cemented sediment grains, the products of pre-existing rocks. And then by far and away, the most common sedimentary rock type. We have a lot of rocks on the surface of our Earth that are being broken down by weathering processes at any one time. They're hugely, hugely variable depending on the climatic environment, physical environment. You can have sedimentary rocks with huge boulders in them, or you might have a sedimentary rock with sand-sized particles, or you might have a sedimentary rock such as this in Suva with very fine-grained particles. You might start off with a granite being weathered on land, which contains feldspar, quartz. If you have a sediment produced not that far away from that granite, you'll still have feldspar and quartz, but because quartz is very resistant and feldspar isn't, if you travel further downstream, you tend to have more quartz than feldspar. So the type of plastic rock you end up with depends on many, many factors: the nature of the pre-existing rock, the transportation distance, the climate. Our chemical sediments, they're made of crystals, and again, they're formed by the precipitation of minerals from solution. A really common type of chemical sediment is called an evaporite, which is formed by the evaporation of water in these salts. Biogenic and biochemical, this is what next week's lecture will focus on, because they're incredibly important in the Pacific. So they're living organisms which extract chemicals from an environment, they build skeletons or shells or bones, and they eventually might be buried to form rocks. And all of these reef rocks here around these South Pacific islands are forming rocks the entire time. So then there's organic, where we actually have living tissues that might be buried. This is a layer of coal, which was initially swampy material formed in an equatorial environment, and this is what we call an oil shale. It's a mudstone so rich in organic matter that you can actually set it on fire. And finally, volcanic plastic, which is built up of volcanic and igneous rock fragments, but I won't touch on those today. I'm mainly going to focus on plastics if I can. You can't really see that here. So we generally talk about fine-grained plastic sediments as mud or silt. So clay or mud are the same thing. Clay is the mineral type. They're very, very fine. They don't really settle out unless we have very low energy. Medium-grained sediments, we're generally talking about sand. They require a little bit of energy to be transported, but you can have a much less drop in energy to deposit them. And our coarse-grained sediments, this is where we're greater than 2 millimeters. And by far and away, our mudstones, so these are sedimentary rocks made out of very fine clay and silt. They're by far and away the most common sediment we find. This is for many reasons, but a lot of igneous minerals eventually chemically weather into clay. And we have so many silicate minerals on land, whether they're grains in sedimentary rocks, or they're in metamorphic rocks, or they're in igneous rocks, and a lot of silicates, should I say, eventually break down to form clay. And clay is very, very fine particles. So just starting with our very, very coarse-grained sediments. So these are sedimentary rocks formed from sediments that are greater than 2 millimeter in grain size. The names we give to them are breccias and conglomerates. If those large fragments are angular, we call it a breccia. If they're quite rounded, we call it a conglomerate. And these distinctions are very, very important. Grain size distinctions are important. Observations like this are important because they all depend on the environment where they were deposited. All of this information tells us something. The fact that we have large plasts tells us something about the energy of the environment. There must have been a lot of energy to transport them in the first place. And also the fact that they're angular, this tells me that it hasn't been transported very much. Whereas this one has been rolled a lot about and been abraded and rounded. So they're very, very different sedimentary environments. And breccias are incredibly common around the South Pacific, where you have landslides. Because you have these steep-sided mountains formed by volcanoes, you have a lot of landslides. So a lot of coarse material can fall downhill, but it's not transported very far, and it just sits there and it gets buried, and it has not been very rounded. Whereas conglomerates are quite common in rivers, where there's constant transport by water, the pebbles are constantly bashing into each other, so you get a lot more landing. So this is an example of a glacial pressure. So, as I said before, when rocks are transported by ice, they don't become rounded because they're not bashing into each other. So if you have a glacier that melts, you tend to have these very angular deposits, such as breccias. Because ice is a very, very good transporting medium. You can transport great big boulders in ice. Water, you need much more energy in the water current to transport boulders of the same size as ice. Mountain streams, you can deposit conglomerates, and also beaches, typical. But these environments are quite rare, where we call these coarse grained sediments. And one really useful thing about these sediments is because we can look at the grains, we can look at these clasts, and we can tell what rock type it is because they're big enough. We can tell the source of that sedimentary rock. So this is called the Sediments conglomerate from near Pacific Harbour. And if you look closely at each rock type, you can tell pretty much which volcanic range it came from. So this ancient river deposit, we know was transported maybe, I think it's northwest, it came from the northwest. So we can reconstruct information about an ancient river just by looking at this, because we can trace this to its source, we can match this rock type to the source rock somewhere else in Fiji. So slightly smaller grains, we come onto our sandstones. So these are grains between 0.062 and 2 millimeter grain size all cemented together. And the shape and the size of grains is important if we're going to know something, if we're going to learn something about the sedimentary environment. In terms of sorting, this is a nice little chart you might take into the field view. And as I said before, an example of something that might be well sorted, constantly being moved around. Beach sands, whereas glacial sands are incredibly poorly sorted. And we can also look at the composition. So we divide sandstones slightly into quartz-rich sandstones, and these are sandstones produced in areas where there's a lot of chemical weathering to remove everything else but the quartz, and also a lot of transportation. Everything else has been removed. They're incredibly common in deserts and beach sands. If you have a lot of feldspar in that sandstone, you know that it has not been transported very far, because feldspar very easily gets broken down. And grey wacky is another type of sandstone. They have a lot of clay. They're incredibly poorly sorted for a sandstone, and they're typical of the deposits around here. And finally, I know I'm listing a lot of things here, but these terms are incredibly important. And we have our very fine-grained sediments that can form in a wide variety of environments, not to mention the seafloor. The seafloor is covered in very fine-grained sediments. As you're transporting from the mountain to the coast, you get rid of a lot of your coarser grains as the current loses energy. Everything that reaches the sea tends to be quite fine-grained. And the very, very fine particles can be transported quite far out to sea. So we have a lot of fine-grained clays in the open ocean. So the open ocean has a lot of these fine sediments in it. Very importantly for agriculture, another environment where we have these fine-grained sediments is on the floodplains of rivers. So where you have a river flowing on reasonably flat land, it can flood seasonally. So this might be normal conditions. This is where it might flood. And as it floods, it deposits some of the sediments, typically the finer grained sediments, because the coarser grained sediments are down here. And clay is actually very important for making soils fertile. So if you have these fine particles of clay, and you're spreading them out on these areas of flat land next to rivers, actually that makes very fertile soils. And it's one of those unfortunate things, that's why people have agriculture on floodplains. Why people build houses on floodplains, as well as the water source and transportation, but the downside is you get flooded. And again, I'm not a petroleum geologist, I'm not interested in that. If I was, then I'd be earning millions of pounds somewhere in Texas. I don't know, I'm not. But in terms of the history of petroleum, mudstones are really, really important. Because if mudstones have a high organic matter content and they get buried in the ocean, so marine organic matter, they can eventually produce oil. And we call that type of mud rock a source rock. But what happens to that oil as it starts to form, because it's liquid, it rises up because it's more buoyant, so it rises up through the crust. And what happens then is it needs to find somewhere, if you're an oil geologist, you need to have a reservoir of it. You don't want the oil to escape to the surface. Now mudstones, these fine-grained particles, they tend to be quite impermeable. They don't let fluids through. So mudstones are incredibly important cap rocks. So not only are they important source rocks, they stop that oil eventually escaping to the surface. The other type of rock that's really important for oil is called a reservoir rock, and it needs to be porous. It needs to have spaces within it that can hold that oil. So the situation oil geologists look for is a nice organic rich mudstone with a nice porous, permeable reservoir rock above it, and a nice impermeable mudstone on the top, which is your cap rock. And this is an example where our sedimentary layers have been folded by tectonic pressure, so they've collected the oil in this reservoir. Mudstones are incredibly important in the oil industry. So finally, when I talk about this, so I'll talk about not only the grains and the composition of those sedimentary rocks, but you can see some really, really nice structures in sediments that can tell you a lot. They can be beautiful, they can tell you a lot about the environment of those sediments. They will provide clues. And the most common type is just bedding. So, as we know, sediments collect under gravity and they form layers, which we call strata, and we can see them in the geological record when they're eroded. Some beds might be millimeters thick, some beds might be tens of meters thick. But this is a nice example of a sequence. These sediments could have been deposited first, followed by those, by those, by those. And each of the changes in the colour and the composition tell us something about a change in the environment. And looking at those beds more closely, sometimes, this is a nice cartoon, you might get coarser grains at the bottom, and then progressively finer grains towards the top of the bed. And then the bed above might have the same thing. This is really common because what happens is when you have a current transporting a mixture of grain sizes, as it starts losing energy, it'll deposit the coarse ones first. As it loses more energy, it'll deposit the medium grain. If it loses more energy, it'll deposit the finer grain. So this is really common in sedimentary layers. We need to call this gradient bedding. And it's really common on the deep sea floor. As I've told you, there are these really steep marine canyons cutting into the continental slope. Sediments collect at the top. They rush downstream when they become unstable down the canyons, and eventually they settle out. And that's what a turbulent current looks like. You can't really see here. But the coarser grains are deposited first, they get finer upwards. Coarser grains, finer upwards. And each one of those beds is a different turbidity current. Cross-bedding can be hard to get your head around. It produces some really beautiful scenery. Essentially, it's where you have, within a bed, you have smaller incline layers. And it's formed from where you have ripples, or you have dunes in a riverbed, or on a beach, or in a desert. And what happens is, say this is our ripple here, our wind or water, whatever it is that's moving grains, picks up grains from this side, and it deposits them on the steeper side. This process continues, picks up grains, deposits them on that side. And what happens is, you build up layers that are at an angle from the normal bedding surface. So within each bed, you have these inclined layers. I think I've got a better diagram on the next slide, hopefully. Yeah, so you have a dune or a ripple. Ripples are small, dunes are bigger. wind water picking up grains here, depositing them on this side. As you pick up more grains here, you're eroding this side, and you're depositing on this side in successive layers. So you build up more and more layers, your ripple migrates this way, and eventually you have an entire bed. An entire bed made up one bed with inclined layers of ripple. We call that cross bedding. And it's really nice because we can tell which way the current is going. If we have our inclined layers pointing this way, we know that the wind or water was coming this way because it was picking up grains and depositing them in layers on this side. And this is just an example of some beautiful scenery that can be caused by, this is an ancient desert in the US. All of these were ancient dunes. All of these individual layers are the inclined layers on one side of the dune. Yeah, incredibly beautiful. Different types of ripples. So if you have a tidal environment where waves are moving water in two directions, they're coming in, they're going out, they're coming in, the ripples are actually symmetrical. So you get deposition on both sides of the ripple. So if we see a ripple that's symmetrical in cross-section, we know that it must have formed in a tidal environment. And you can't see the photos here, but these are all ripples formed somewhere where the waves are still affecting the sediment below. And these are some nice examples of some ripples being preserved in rocks. Again, we'll see that on the field trip hopefully. If very fine sediment is exposed to air and it dries out, it can form these polygonal cracks called mud cracks. We can also see those in the rock record, telling us that that sediment was formed somewhere where it was allowed to dry out. And also, another nice thing we can see in sediments is where animals living in that sediment have churned up the sediment, they've burrowed into the sediment, and we can see that preserved in the rock. And they can tell us a lot about what was living in that sediment previously. So yeah, sorry I was a bit of a rush today. I'll be less sick next week. But yeah, just to summarise today's lecture, sedimentary rocks form from sediments. Important processes you need to learn about are weathering, erosion, transportation, and burial and implementation. The transportation of sediments can cause them to be sorted. It can cause the grain size to be reduced. It causes them to be more round. And I've introduced plastic sediments. Next week I'll talk about the other sediment types. We describe them according to their grain size, and I've described some sedimentary structures that can tell us about the environment and deposition. I'll put all these notes online as well as